Alright, so a rectangular loop of wire is 15 centimeters long and 3 centimeters high. The wire has a resistance of 0.03 ohms and moves at a constant speed of 8 meters per second to the right. It emerges from an area of uniform magnetic field of 1.2 Tesla and emerges into an area of negligible magnetic field. What is the direction and magnitude of the conventional current, and what force would you have to apply to make the loop move at this constant speed? Well, there's a couple of things that happen first. Because it's in this magnetic field, it's going to polarize. How do we know that? Well, from the magnetic force law, we know that F, there's a little bit of eraser dust there, F is equal to Q times V cross B. So what's going to happen is V is this way, so we've got V cross B, so we know that the positive charges are going to go up towards the top of this wire loop here. So it's going to be positive up here and negative down here. So the next thing we're going to need to do is, because this is polarized, there's going to be a current. And it's because it's in a magnetic field and there's a magnetic force on it, there's going to be a current running through it. So we're going to use the right-hand rule to determine the direction of the current. Well, in order to do that, we put our thumb in the direction of the magnetic field and rotate it around. Now we know that the current is going, my wrist is going to break, this way. So that means that I is like this. So here we go. Using the right hand rule, the thumb is in the direction of the current. It's clockwise. See? Alright, so the next thing. In order to determine the current, first we have to solve for the motional EMF. Well, we know that the potential or motional EMF is equal to V, or the drift speed, times B, the magnetic field, times the height of the wire is what we're going to use because of the cross-sectional area. Well, yeah. So, we'll just plug in some constants, or not constants, our given values. So it's going to be 8 meters per second, 1.2 Tesla, and I already converted these 3 centimeters to 0.03 meters. I just forgot to write it down. And that'll give us a total of 0.288 volts. It's pretty good. Alright, so then we're going to use Ohm's law to solve for the actual magnitude of the current. So how do we do that? I is equal to delta V over R, where R is the resistance. Well, the resistance was given, and we just solved for delta V, so we're just going to plug that in. 0.288 volts over 0.3 ohms will give us 0.96 amps flowing through this loop of wire, which is pretty good. So now we solve for the force. We know that the magnetic force on a short wire is represented by F equals I, which is the current, times delta L, which is the length, times B. So, cross B, sorry. And the cross product is I, L, B sine theta. Well, since it's going to be into the plane, it's going to be the sine of 90 degrees. So what we're going to solve for is, so it's just 1, essentially. You could probably just omit it from the whole calculation, but it's going to be 0.96 amps times 0.03 meters times 1.2 Tesla is equal to 3.45 times 10 to the negative 2 newtons in the right direction. Thank you.